The Octet Rule. According to the Octet Rule, atoms will lose, gain, or share electrons in order to achieve a noble gas electron configuration. So for example, if we have two fluorines with 7 electrons each, they will share that one unpaired electron to form a bond. Each F counts both shared electrons to feel as though it has a neon configuration. Only valence electrons contribute to bonding. The valence electrons in fluorine, for example, being your 2s2 2p5 electrons. Only two valence electrons participate in the formation of the F2 bond. On the left here, we see the electrons shown in blue and red for the two different atoms, whilst on the right here, we represent the two shared electrons with a dash. When you see a dash between two atoms in any molecule, you should assume that it is two electrons being shared. The pairs of valence electrons not involved in bonding are called lone pairs. Lewis structures. A Lewis structure is a representation of covalent bonding. Shared electron pairs are shown either as dashes or as pairs of dots. Lone pairs are shown as pairs of dots on individual atoms. So on the left here we see all our electrons shown as dots, and we've highlighted which atoms see which electrons. So you'll notice that both hydrogens have 2 electrons and oxygen has 8. We can also represent the shared electrons as dashes. So on the right we see the structure of water where the shared electrons are shown as dashes. These shared electrons are of course referred to as bonds. Multiple bonds. In a single bond, atoms are held together by one electron pair, as seen in water, H2O. You have one pair of electrons being shared by the hydrogen and the oxygen, so we can represent that as a dash, a single dash being a single bond. In a double bond, atoms share 2 pairs of electrons. So in carbon dioxide, we'll notice that the carbon is sharing 4 electrons with each oxygen. 4 electrons being 2 pairs of electrons, implying 2 separate bonds. This double bond can be represented as 2 dashes. A triple bond occurs when atoms are held together by 3 electron pairs, such as in nitrogen gas. We see that 6 electrons are being shared in between 2 nitrogens. That's 3 pairs of electrons, meaning a triple bond. Bond length is defined as the distance between the nuclei of 2 covalently bonded atoms. Table 6.1 shows the average distances of different types of bonds for comparison's sake. Just have a quick look at these numbers and try to see any patterns. Multiple bonds tend to be shorter than single bonds. So for a given pair of atoms, triple bonds are shorter than double bonds, and double bonds are shorter than single bonds. The trend can be seen with nitrogen, where the nitrogen-nitrogen triple bond is only 110 picometers, the nitrogen-nitrogen double bond is 124 picometers, and the nitrogen-nitrogen single bond is 147 picometers. The shorter multiple bonds are also stronger than single bonds. We quantify bond strength by measuring the quantity of energy required to break it. So for example, if you have a hydrogen gas, 2 hydrogen atoms bonded together, the bond energy is 436.4 kilojoules per mole, which is the energy required to split the 2. We will be examining this more in detail in chapter 10. But as a brief summary, you should remember that multiple bonds are stronger than single bonds, and multiple bonds are shorter than single bonds, also giving the general trend that the shorter the bond, the stronger it is, and the longer the bond, the weaker it is. It's a nice point of reference. Electronegativity and polarity. There are 2 extremes in the spectrum of bonding. Covalent bonds occur between atoms that share electrons, and ionic bonds occur between a metal and a nonmetal and involves ions. Bonds that fall between these extremes are polar. In polar covalent bonds, electrons are shared but not shared equally. In this case, we use delta to denote partial charges on the atoms. So as a summary, bottom left, pure covalent bonds, these have neutral atoms held together by equally shared electrons. Center, you have the polar covalent bond, which is partially charged atoms held together by unequally shared electrons, and we show these partial charges with a delta plus and a delta minus on the atoms. And then finally you have ionic bonds, where oppositely charged ions held together by electrostatic attraction, like full charges. Electron density maps show the distribution of charge. So electrons spend a lot of time in red and very little time in blue. So if we look at the hydrogen gas, it is a nonpolar covalent bond. All the electrons are in the middle of the molecule, and therefore the electrons are shared equally. We can then have hydrogen fluoride, which is a polar covalent bond, where clearly the electrons are only to one end of the molecule, and there's practically an absence of electrons on the other. Here, electrons are not shared equally and are more likely to be associated with the fluorine because it's more electronegative. And then finally, with sodium fluoride, we can actually tell the atoms apart in the shape of the molecule, and we notice that the electrons are most certainly towards one end. Therefore, the electrons are not shared, but rather transferred from the sodium to the fluoride, making this sodium fluoride an ionic compound with an ionic bond. Electronegativity is the ability of an atom in a compound to draw electrons to itself. So here we have a nice scaled periodic table showing the differences in electronegativity. You will notice that electronegativity seems to increase from left to right and also increase from bottom to top, with the most electronegative atom being fluorine and the least electronegative elements being the bottom of group 1, cesium and francium. Please memorize this trend, and if you want a mantra, just remember that fluorine is the most electronegative element and oxygen is the second most electronegative element. Work with that. Electronegativity varies with atomic number. We can clearly tell the trend being that the electronegativity increased from left to right, taking a little detour in the D block, as we can see in the second two on the right. Another one to note is, of course, hydrogen, not quite following group 1 pattern, and has an electronegativity just over 2, which is slightly more electronegative than boron and a bit less electronegative than carbon. And finally, a more general comment, you may notice that the scale is pretty much between 1 to 4. So keep in mind what kind of ranges each group is found in. There is no sharp distinction between nonpolar covalent and polar covalent, or between polar covalent and ionic. The following rules help distinguish among them. A bond between atoms whose electronegativities differ by less than 0.5 is generally considered purely covalent or nonpolar, whilst a bond between atoms whose electronegativities differ by the range of 0.5 to 2.0 is generally considered polar covalent. And finally, a bond between atoms whose electronegativities differ by 2 or more is generally considered ionic. Dipole moment, partial charges, and percent ionic character. So, looking at this hydrogen fluoride electron density diagram, we see that the electrons tend to spend very little time on the hydrogen side, hence the blue color, and the electrons seem to spend a lot of time on the right hand side where the fluorine is, shown in red. We can use an arrow to indicate the direction of electron shift in polar covalent molecules. We show an arrow pointing towards the fluorine because that's where the electrons are going. The consequent charge separation can be represented as deltas to denote partial positive or negative charge. So because the electrons are flowing towards the fluorine, you should have partial negative charge on that side, because remember, electrons are negative. Whilst hydrogen, not having those electrons per se, will get a partial positive charge because of an absence of electrons. A quantitative measure of the polarity of a bond is its dipole moment, represented through the symbol mu. So mu equals Q, the charge, times R, the distance between the charges. The dipole moment mu is always positive and expressed in debye units. So 1D being 3.336 times 10 to the negative 30 coulomb meters, where C is coulomb and M is meter. In this table here, we can see the bond lengths and dipole moments of the hydrogen halides. You'll notice as the bond length increases, the dipole moment seems to decrease. Of course, if we look at the equation itself, this may indicate that the electronegativity, or the charge, is definitely more important than the distance for this dipole moment. Although the designation covalent, polar covalent, and ionic can be useful, sometimes chemists wish to describe and compare chemical bonds with more precision. Comparing the calculated dipole moment with the measured values gives us a quantitative way to describe the nature of a bond using the term percent ionic character. Percent ionic character being the observed dipole divided by the calculated, assuming discrete charges, dipole times by 100%. The figure below demonstrates the relationship between percent ionic character and the electronegativity difference in a heteronuclear diatomic molecule. You will notice that the higher the electronegativity difference, the higher percent ionic character there tends to be. But what should also stand out is that even with something like potassium fluoride, where you have a very low electronegativity potassium with the highest electronegativity fluorine together, they still do not have 100% ionic character, even though we would call that molecule an ionic compound and we would assume the bond is an ionic bond. Drawing Lewis structures. Follow these steps when drawing Lewis structures for molecules and polyatomic ions. Step 1. Draw the skeletal structure of the compound. The least electronegative atom is usually the central atom. Draw a single covalent bond between the central atom and each of the surrounding atoms. Step 2. Count the total number of valence electrons present. Add electrons for negative charges and subtract electrons for positive charges. Step 3. For each bond in the skeletal structure, subtract 2 electrons from the total valence electrons. And step 4. Use the remaining electrons to complete octets of the terminal atoms by placing pairs of electrons on each atom. Complete the octets of the most electronegative atom first. Step 5. Place any remaining electrons in pairs on the central atom. And step 6. If the central atom has fewer than 8 electrons, move one or more pairs from the terminal atoms to form multiple bonds between the central atom and the terminal atoms. If you follow these steps, you will always get the correct Lewis structure. But I guess, what does it all mean? Let's check it out. Say we get asked to draw the Lewis structure for ClO₃-. Well, step 1 was draw the skeletal structure of the compound. The least electronegative atom is usually the central atom. Draw a single covalent bond between the central atom and each of the surrounding atoms. Well, if you only have chlorine and oxygen, oxygen being the second most electronegative atom only behind fluorine, it means that chlorine is the less electronegative atom out of these two. Therefore, chlorine needs to be drawn in the middle, and we should add 3 oxygens to it with single bonds. Step 2. Count the total number of valence electrons present, add electrons for negative charges, and subtract electrons for positive charges. Well, we have one chlorine. One chlorine has 7 electrons. We have 3 oxygens. Each oxygen has 6 electrons, so that would be 18 electrons. And we have a negative charge, so that would be 1 extra electron, to give us a total of 26 valence electrons in this polyatomic ion. Step 3. For each bond in the skeletal structure, subtract 2 electrons from the total valence electrons. we have 3 bonds. Each is 2 electrons, giving us 6 electrons. There's supposed to be 26 valence electrons, but we subtract the 6 that are already shown bonding to give us 20 electrons left over. These are the electrons that have not been forming bonds yet. Step 4 stated that use the remaining electrons to complete octets of the terminal atoms by placing pairs of electrons on each atom. Complete the octets of the most electronegative atoms first. Well, as stated before, 6 electrons are used in single bonding. Therefore, we have 20 electrons that must be placed in the structures starting with the terminal atoms. Well, we start putting our electrons in to give 8 electrons to each atom. So in oxygen's case, it already has 2 bonded to the chlorine, so we need to add 6 in each. This adds a total of 18 electrons onto the molecule. Therefore, we have used up 24 of the 26 electrons available. Note the 18 from the dots and the 6 from the dashes, giving us 24. So we have 2 electrons left. Step 5 said that place any remaining electrons on the central atom. So therefore, as we have 2 electrons remaining, we must add them to the chlorine. And voila, we have the Lewis structure of ClO₃-. Now the Lewis structures for polyatomic ions are enclosed by square brackets to emphasize that the charge is somewhere on the molecule, but we're not specifying where. Step 6 is here to check the structure. So if the central atom has fewer than 8 electrons, move 1 or more pairs from the terminal atoms to form multiple bonds between the central atom and the terminal atom. Well, let's count how many electrons each atom has, starting with the middle. Well, chlorine has 3 bonds, so that is 6 electrons, plus the 2 extra electrons as a lone pair, giving us an octet, i.e. 8 electrons around chlorine. As we already added electrons to make 8 on each oxygen, this means that all atoms already have an octet in this structure. So, no need to fix anything. This is the structure. Here we have a table going through step by step how to get to the Lewis structures of these 5 compounds, with varying scenarios of whether you're going to need multiple bonds or not. I recommend practicing and giving it a go. Cover up the table as you work on each structure and then check your work. Lewis structures and formal charge. Formal charge can be used to determine the most plausible Lewis structure when more than one possibility exists for a compound. The formal charge is valence electrons minus associated electrons. To determine associated electrons, all the atom's non-bonding electrons are associated with the atom, and half the atom's bonding electrons are associated with the atom. So you may get a question that says, determine the formal charges on each oxygen atom in the ozone molecule O3. You may be asked to draw the Lewis structure, or you may be given it. Here is it given to you. Right? We would focus on each atom in the molecule, starting with the oxygen to the left. And we will notice that it has 4 unshared electrons and a double bond, meaning that there are 4 shared electrons, 2 for each dash, recall, which you divide by 2, because only half of those are associated with the atom we are talking about. So 4 unshared plus 4 shared divided by 2 gives you 6 electrons. The middle oxygen has 2 unshared electrons and 3 dashes, meaning 6 shared electrons. We divide that by 2. 2 unshared electrons plus 6 divided by 2 gives you 5 electrons. And for the third atom, we have 6 unshared electrons and 1 dash. So that's 2 shared electrons divided by 2 gives us 7 electrons. We now do the formal charge calculation, which was the valence electrons minus the associated electrons, giving us for the leftmost oxygen 6 valence electrons minus 6 associated with the atom to give us a formal charge of 0. For the middle oxygen, 6 valence electrons, 5 associated electrons, so 6 minus 5 is plus 1, and the furthest to the right, we have 6 valence electrons minus 7 associated electrons to give us a charge of -1. When there is more than one possible structure, the best arrangement is determined by the following guidelines. 1. A Lewis structure in which all formal charges are 0 is always preferred. 2. Small formal charges are preferred to large formal charges. And 3. Formal charges should be consistent with electronegativities, i.e., a negative charge should be on the most electronegative atom and a positive charge on the least electronegative atom. So let's compare carbon dioxide, OCO. We could have an oxygen double bonded to the carbon on each side, or we can have an oxygen triple bonded to a carbon and single bonded to a carbon. You will notice that with the oxygen triple bonded to carbon and single bonded to carbon, you will have a positive charge on one oxygen and a negative charge on one oxygen. Whilst if you have double bonds from both oxygens to carbon, there's 0 formal charge. Therefore, this is a better structure based on formal charges. Resonance. A resonance structure is one of 2 or more Lewis structures for a single molecule that cannot be represented accurately by only one Lewis structure. So say with ozone, we said that the furthest one to the left has a 0 charge, the middle one has a positive charge, and the one to the right has a negative charge. Well, in fact, they can shift those electrons around to give you the same structure, but where the one on the left is the negative, the middle one is positive, and the one on the right is neutral. Well, in fact, both of them exist at the same time, and when we draw our electrons on one or another, we are just showing a snapshot of an extreme state, as in we are saying the electrons are specifically here, but technically they're moving around throughout the molecule. Resonance structures are a human invention. Resonance structures differ only in the position of their electrons. The carbonate ion is another example of resonance. So you will notice that we have a carbon with a double bond to one oxygen and single bond to 2 oxygens with a -2 charge overall. Well, that double bond can shift thanks to resonance. So in other words, we can represent that double bond between carbon and oxygen between any of the oxygens, because in reality, all of these resonance structures exist at the same time, and therefore all of the carbon-oxygen bonds are somewhere in between a single and a double bond, but that would be difficult to depict. Whilst here at the bottom we have the skeletal structure of benzene showing resonance, and we can see that the double bonds can flow around between different carbons and swap places. Exceptions to the octet rule. Incomplete octets. Exceptions to the octet rule fall into 3 categories. 1. The central atom has fewer than 8 electrons due to a shortage of electrons. So for example, beryllium dihydride, there are only 4 total valence electrons in the system. Elements in group 3A also tend to form compounds surrounded by fewer than 8 electrons. For example, boron reacts with halogens to form compounds of the general formula BX3, having 6 electrons around the boron atom. Once again, short of the total of 8 electrons required. 2. The central atom has fewer than 8 electrons due to an odd number of electrons. So for example, NO2, there are only 17 valence electrons in the system. Molecules with an odd number of electrons are sometimes referred to as free radicals. And you can recognize any free radical by that single electron on any of the atoms. And 3, the central atom has more than 8 electrons. So for example, this sulfur hexafluoride has 6 bonds to sulfur corresponding to 12 electrons. Therefore, this sulfur has 12 instead of the 8. Atoms in and beyond the 3rd period can have more than 8 valence electrons. In addition to 3s and 3p orbitals, elements in the 3rd period also have the 3d orbitals that can be used in bonding. Another exception to the octet rule is found with Lewis acids and Lewis bases. So let's look at this example here. So the bond between boron and nitrogen has both the electrons contributed by the nitrogen atom. This type of bond is a coordinate covalent bond or a dative bond. This type of bond formation is an example of a Lewis acid-base process. So the nitrogen donates its protons to the boron to give boron a full octet. The BF3 in this case is a Lewis acid, as it's accepting a pair of electrons, whilst the NH3, ammonia, is a Lewis base, as it's donating a pair of electrons. That's pretty much the definition of Lewis acids and Lewis bases.